Alright, let's go. Number 10. The Modal Fictionalism Rebuttal. In the early 1990s, a young philosopher named Gideon Rosen sat down not to attack modal realism, but to save modal logic from it. He wanted a way to keep talking about possible worlds without the metaphysical baggage. The standard model of philosophical logic predicts that when we say it's possible the sky could have been green, we're just using a convenient shorthand. Nothing extra needs to exist. Rosen found something else. When he tried to build a fictionalist account that treated possible worlds as pure invention, useful lies we tell to make logic work, the mathematics resisted him. The sentences describing fictional worlds behaved exactly like sentences describing real ones. In his 1990 paper Modal Fictionalism, published in the journal Mind, Rosen showed that no consistent boundary separates the grammar of pretend worlds from the grammar of real ones. Every attempt to mark the difference collapsed back into the thing it was trying to avoid. Philosophers tried adding a hereby operator to flag fiction. It failed under nested modal claims. They tried restricting fictionalism to a single storyteller's voice. It failed once two people disagreed about the same possible world. They tried grounding the fiction in brain states instead of external reality. It failed because brain states are, themselves, physical facts requiring the same explanation. Every fix imported the very realism it was built to reject. If the sentence "you could have been a different person" is only fiction, why does it hold together with the same rigor as a fact? Why does your own sense of what almost happened to me refuse to dissolve when philosophers stop believing in it? Nobody has found the scene where invented and existing possibility come apart. That scene was supposed to be simple. It has never been found. Number 9. The Anthropic Shadow. In 2008, philosopher Nick Bostrom and physicist Milan Irkovi were working on ordinary risk assessment, trying to calibrate how often civilization-ending events like asteroid impacts or supervolcanic eruptions actually occur. Statistics predicts you can estimate a disaster's true frequency by counting how often it has happened in the observable past. That's the entire foundation of actuarial science and geological risk modeling. Bostrom and Irkovi found the method breaks for the worst disasters of all. In their paper Anthropic Shadow, Observation Selection Effects, and Human Extinction Risks, they showed that any event catastrophic enough to have ended human observers simply cannot appear in our historical record. No matter how common it actually is, we only exist to count the disasters that didn't kill everyone. Scientists proposed correcting for this using nearby star systems as a control group. That failed, because we cannot confirm whether life arose and was erased elsewhere. They proposed using geological deep time before humans existed. That failed too, since pre-human extinction events don't tell us what thresholds our specific branch of survival. They tried Bayesian reweighting of impact crater frequency. It only shifted the uncertainty, it never removed it. This means humanity's estimate of its own extinction risk from an asteroid, a gamma-ray burst, or a supervolcano may be silently, catastrophically too low. Every year you've been alive to read a risk report is a year in which the worst outcome, by definition, could not have been recorded. You are alive today partly because of a statistic you are structurally unable to trust. We can't measure the disasters that would have erased the person counting them. Number 8. Eternal inflation's bubble collisions. Cosmologists in the early 2000s were not hunting for other universes. They were trying to explain a much smaller problem: why the cosmic microwave background looks so uniform across the sky. The standard model of eternal inflation predicts our universe is one bubble nucleating out of an inflating background, a background that never stops producing new bubbles elsewhere. If two bubbles form close enough together, the model predicts a faint disc-shaped scar should appear in the CMB where they brushed against each other. In 2011, Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris published first observational tests of eternal inflation in Physical Review Letters, scanning MAP satellite data for exactly that signature. They found candidate disks. 4 of them, statistically significant enough to publish. Then the follow-up work began, and the failures started. Independent teams reanalyzing the same patches found the disks were consistent with ordinary noise once foreground contamination was modeled more carefully. Planck's satellite data, sharper than MAP, failed to confirm the strongest candidates. Researchers tried adjusting the expected collision geometry. The signal didn't strengthen. They tried searching polarization data instead of temperature data. Still nothing conclusive. The theory that predicted these scars was never disproven. The scars themselves simply refused to resolve into certainty either way, if eternal inflation is correct. Another universe brushed against the birth of everything you have ever known, and the evidence is sitting in data we already collected, unresolved, waiting. The scar might already be sitting in a satellite archive nobody has proven is real. Number 7. Vacuum decay bubbles. Sidney Coleman was working on the mathematics of quantum tunneling and field theory, a fairly dry corner of particle physics, when he and Frank DeLucia turned their attention to what happens if the vacuum of space itself isn't stable. The Standard Model predicts our vacuum sits in the lowest energy state possible, a permanent, unshakable floor beneath reality. In their 1980 paper, Gravitational Effects on and of Vacuum Decay, published in Physical Review D, Coleman and DeLucia showed the floor might not be the floor at all, just a false minimum sitting above a deeper, truer vacuum. Then in 2012, physicists including Giuseppe de Grassi and collaborators published Higgs mass and vacuum stability in the Standard Model at ENLO in the Journal of High Energy Physics, calculating that using the measured Higgs boson mass of roughly 125 giga-electron volts. Our vacuum sits precariously close to that lower, unstable state. Physicists proposed the vacuum was simply metastable on timescales far longer than the age of the universe, which technically resolves the danger but not the unease. They proposed new physics beyond the Standard Model could stabilize it. No such physics has been confirmed at the Large Hadron Collider. They proposed the calculation itself contained errors. Repeated independent recalculations kept landing in the same danger zone. If a bubble of true vacuum nucleates anywhere in the universe, it expands at the speed of light in every direction, rewriting the laws of physics as it goes. You would never see it coming, because nothing can outrun it, not even the warning. There would be no warning, because the warning travels at the same speed as the end. Number 6. The no-boundary proposals alternate histories. In 1983, James Hartle and Stephen Hawking were trying to solve a much narrower problem. What initial condition to plug into the equations of quantum cosmology so the universe wouldn't require an arbitrary starting point? Standard cosmology predicts you need a boundary condition, some fixed moment where time begins and the equations switch on. Hartle and Hawking proposed removing the boundary entirely, treating the early universe's geometry as smoothly curving into itself, the way a globe has no edge despite being finite. Their paper, Wave Function of the Universe, published in Physical Review D in 1983, modeled the universe's beginning using a sum over every possible geometric history simultaneously, weighted by probability, exactly like the way a single particle explores every path at once in quantum mechanics. Scientists tried to interpret this as merely a calculational trick, a way to get a smooth number out of the math without literal meaning. That interpretation collapsed once cosmologists applied the same framework to predict actual observable features of the cosmic microwave background. And it worked. They tried restricting the sum over histories to only our observed outcome. That defeats the entire purpose of the model, since a single fixed history is precisely what Hartle and Hawking removed. If the framework is taken literally, every possible early universe you could have had, every different set of physical constants, every failed cosmos that never produced stars, existed in quantum superposition before your branch became classical and solid. Something that was never fully decided crystallized into the specific reality holding your body together right now. Nobody can say when the superposition became you instead of something else. Number 5. Modal Realism. David Lewis was a philosopher working on the truth conditions of counterfactual statements. Sentences like, if you had left 5 minutes earlier, you would have missed the crash. Standard philosophical logic treats these as useful fictions, ways of reasoning about hypotheticals without requiring anything to actually exist. Lewis found the fictions kept behaving like facts under formal analysis, and rather than patch the inconsistency, he followed it. In his 1986 book On the Plurality of Worlds, Lewis argued that every logically possible world is exactly as real, as solid, and as physically concrete as this one. populated by counterparts of you living out every coherent variation of your life. This wasn't metaphor for Lewis. He meant it with the same seriousness a physicist means electron. Critics proposed restricting real to only causally connected worlds, which would exclude Lewis's other universes by definition. That move simply redefined the word instead of answering the objection. They proposed an epistemic argument that we can never verify these worlds, so we shouldn't believe in them. Lewis countered that unobservability was never previously accepted as disproof in physics, citing the then unconfirmed existence of black holes as a parallel case. They proposed Occam's razor, that simpler theories are better. Lewis argued modal realism was in fact simpler, since it required no special primitive concept of possibility, only existence itself, applied everywhere logic permits it. If Lewis was right, there is a version of you, right now, in a fully concrete world, who made the one decision you still regret differently. That version of you is not a thought experiment. Under this framework, it is a neighbor you will never meet. Number 4. The landscape of string theory. In the late 1990s, string theorists were trying to solve a technical embarrassment: why string theory produced not one clean vacuum solution matching our universe, but a bewildering number of mathematically valid alternatives. The standard hope had been that a single unique solution would emerge and confirm string theory as the true theory of everything. Physicists Raphael Bousso and Joseph Polchinski, in their 2000 paper Quantization of Four-Form Fluxes and Dynamical Neutralization of the Cosmological Constant in the Journal of High Energy Physics, found the opposite. The extra dimensions of string theory could be folded, or compactified, in an enormous number of geometrically distinct ways, each producing a different set of physical constants. Leonard Susskind formalized the scale of the problem in his 2003 paper, The Anthropic Landscape of String Theory, estimating the number of distinct stable vacuum solutions at roughly 10 to the 500th power. A number so large that comparing it to the number of atoms in the observable universe understates it by hundreds of orders of magnitude. Physicists proposed further symmetry principles would eventually narrow the landscape down to one true vacuum. None have been found in 2 decades of searching. They proposed string theory was simply incomplete and a deeper formulation would fix it. No such formulation has emerged. They proposed anthropic reasoning, that we simply inhabit whichever vacuum permits observers, which resolves the selection problem but abandons the original dream of a unique, inevitable universe. If string theory is correct, the specific strength of gravity, the mass of the electron, the constant governing chemistry itself were not required by any deep law. They were drawn, effectively at random, from a landscape too vast to fully survey. Nothing had to make your chemistry possible. It simply happened to land that way. Number 3. Boltzmann Brains. In 2002, Lisa Dyson, Matthew Kleben, and Leonard Susskind were investigating a routine question in cosmology. What happens to entropy in a universe with a positive cosmological constant that expands forever? The standard thermodynamic model predicts entropy should increase smoothly as the universe cools, eventually settling into a stable, low-activity state called heat death. Dyson, Kleben, and Susskind found something the equations refused to smooth over. In an eternally expanding de Sitter universe, given infinite time, random quantum fluctuations in the vacuum will eventually assemble matter into any configuration permitted by physics, no matter how improbable, simply because infinite time makes improbable things inevitable. Their paper, Disturbing Implications of a Cosmological Constant, published in the Journal of High Energy Physics, calculated that a fully formed, momentarily conscious brain, assembling itself directly out of vacuum fluctuations, complete with false memories of a life it never lived, is vastly, overwhelmingly more probable than an entire ordered universe like ours assembling the slow, structured way. Physicists tried excluding these Boltzmann brains as unphysical anomalies. That move requires an arbitrary cutoff with no principled justification. They tried modifying the measure used to calculate probabilities across infinite space. Every proposed measure either reintroduced the problem or broke some other established result. They tried appealing to the low overall entropy of the early universe as the true explanation for our ordered existence instead. That explains why a universe like ours could exist, but not why, statistically, you should expect to be a real product of it rather than a fluctuation. If the reasoning holds, the overwhelmingly likely outcome of the physics you're being told about right now is not the ordered cosmos you're picturing. The overwhelmingly likely outcome is a mind exactly like yours, and nothing else. Flickering into existence and back out again. Number 2. The mathematical universe hypothesis. In 1998, physicist Max Tegmark was working on a modest classification project, cataloging the different types of multiverse proposals already circulating in cosmology, sorting them into tidy categories for a review paper. The standard assumption underneath all of them was that mathematics describes physical reality, that equations are a language we use to talk about something separate from the equations themselves. Tegmark found he could not locate the seams separating the description from the thing described. In his paper, Is the Theory of Everything Merely the Ultimate Ensemble Theory? Published in Annals of Physics and expanded in his 2007 paper The Mathematical Universe and Foundations of Physics, Tegmark proposed that physical existence and mathematical existence are not two things at all. Every self-consistent mathematical structure, he argued, is a physical universe, ours included, and the reason our universe seems to obey elegant. Discoverable laws is simply that it is those laws, with nothing underneath. Physicists proposed this was untestable and therefore not real physics. Tegmark countered that the hypothesis makes a testable prediction, that we should expect to find our universe governed by comparatively simple symmetric laws rather than arbitrary ones, which is exactly what physics keeps finding. They proposed conscious observers require something beyond pure mathematical structure, some additional ingredient. No one has identified what that ingredient would be, or why it would be needed at all. They propose the hypothesis proves too much, since it implies every consistent structure exists whether or not it resembles anything like a habitable universe. Tegmark accepted that consequence rather than retreating from it. If Tegmark is correct, you are not a physical object described by mathematics. You are a mathematical structure, and the sensation of reading this sentence is what that structure feels like from the inside. Number 1. The Tegmark Level 4 Multiverse. Tegmark did not stop at proposing our universe was mathematical. He was trying to answer one final narrower question left over from his earlier work: why our particular universe exists among the merely possible ones. The standard multiverse proposals at the time, inflationary bubbles, string theory's landscape, quantum branching, each still assumed some underlying physical process generating the different universes, some engine doing the producing. Tegmark found that assumption was the last thing left to remove. In his 2003 Scientific American article Parallel Universes, and his 2014 book Our Mathematical Universe, Tegmark argued that if mathematical existence and physical existence are identical, then every mathematically self-consistent structure exists, full stop, with no generating process required, because existence is simply what consistency is. This includes universes with different numbers of spatial dimensions, different logical foundations, structures so alien that human minds may lack the capacity to model them at all. Scientists proposed restricting this to elegant or computable structures only. Tegmark noted this reintroduces an arbitrary rule with no basis inside the hypothesis itself. They proposed the sheer scale collapses under its own weight, that infinite unrestricted existence explains nothing, because it fails to predict anything is more likely than anything else. Tegmark's response was that this is precisely why we should expect to find ourselves in a comparatively simple, orderly universe among the infinite alternatives, since minds capable of asking the question require enough structure to exist in the first place. Nobody has found the flaw that stops the argument. If Tegmark is right, somewhere in that unbounded totality is a mathematically consistent structure identical to this exact moment, except that you stop reading this sentence one word earlier than you actually will. There is no way to determine, from inside this sentence, which structure you are currently the feeling of. 10 entries. 10 separate teams of scientists working on 10 unrelated ordinary problems. None of them went looking for the edge of reality. They found it anyway, buried inside cosmic background radiation, buried inside the mass of a single particle, buried inside a philosopher's sentence about a 5-minute head start. The universe is not confused about any of this. The equations do not hesitate, do not apologize, do not soften the implication for the reader. We are the ones still catching up to what our own best-tested theories have been quietly implying the whole time. Every item on this list sits not at the fringe of physics, but at its most trusted center. If you want to see more videos like this, click the video on screen now.